Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by COMSOL, Mixer Simulations, Modeling Non-Ideal Reactors and Mixers. Our speakers are Ed Fontes and Valerio Mara. Ed Fontes is the Chief Technology Officer at COMSOL. He has been with COMSOL since 1999 and was previously the lead developer for the CFD heat transfer and chemical engineering products. He received his PhD in chemical engineering from the Royal Institute of Technology, Stockholm. Valerio Mara is the marketing director at COMSOL in Burlington, Mass. Previous roles include working in applications, technical support, and sales. He has been at COMSOL since 2008. Valerio received his PhD in fluid machines and energy systems engineering and his Master of Science in nuclear engineering, focusing on numerical methods for CFD. One quick note before I turn this session over to Ed Fontes and Valerio Mara. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I'd like to welcome Ed Fontes and Valerio Mara.
Thank you, Pam. So I'm going to share my screen now. I hope you can see my slides.
I can see them.
Thank you. Excellent. So thank you very much for attending this webinar about non-ideal reactors and mixes in COMSOL, more specifically in the CFD, chemical reaction engineering and mixing modules. So this flowchart here shows a typical modeling strategy when using COMSOL in order to model chemical reactors. So a good way to start is to start with a perfectly mixed system in order to figure out the chemical kinetics, the reaction mechanism. So you set up a hypothesis about the chemical reaction mechanism, and then you set up a model in COMSOL and compare to the experimental results. If you have agreement, then you can continue to the space-dependent models. If you don't have that, then probably if you have a disagreement with experimental results and the model results, then you probably have to calibrate your reaction kinetics, or you have to completely change the reaction mechanism. But once you have a validated reaction mechanism, then you introduce the complications that space-dependent model involve. And modeling the transport equations, the transport of momentum, energy, and mass, and also to keep track of each individual material balance and their reactions. And so COMSOL has the modules that are specialized for specifically this type of modeling strategy, and that's the chemical reaction engineering module in combination with the CFD module. So if you look at the so-called interfaces that you get when modeling, when you have the chemical reaction engineering and the CFD module, then you see that you have this chemical species transport interfaces for transport of diluted species, also for transporting concentrated solutions. And you have also transporting of chemical species in porous media, which we will not discuss that much in today's presentation, but where we have a specific webinar about. Then for momentum transfer, you have the usual type of fluid flow. Pam or somebody else is not muted, so I hear somebody in the background all the time. Can you please mute yourself?
I was muted, but I'll mute again, and I will go ahead and mute.
Okay, good. So if you look at the momentum transport equations, we have single-phase flow, multiphase flow, and also porous media flow. We also have ready-made couplings between, for example, for non-isothermal flow and reacting flows, which are really basically just a fully coupled problem with momentum equations, mass balances, energy balances, and in reacting flow also material balances. In the heat transfer interfaces, which are the energy transport equations, you can combine heat transferring fluids and also heat transfer in solids. For conjugate heat transfer, if you want to model, for example, a metal heater in combination with fluid flow, then you can combine that. Specifically, you can have surface-to-surface reaction, and surface-to-surface reaction will participate in media if you have the heat transfer module. But for radiation surface to ambient, that is actually included in the reaction engineering module and in the CFD module. So if we go back to our little flow chart here and look at the space-independent models that we have, typically this would be a model of a lab-scale reactor where you have full control of mixing, so you know that you have a perfectly mixed system. So the only variations that you have are in time. So you might have composition variations in time, temperature variations in time, but the distribution of temperature and composition is fairly uniform in space. And so that type of model setup we have in COMSOL the reaction engineering interface, which you just type in the chemical equations, and the material and energy balances are automatically defined. Actually, the equations are automatically set up under the hood, both the energy balances and the material balance for each species. And then, in order to go to the next step in the chart here to model a space-dependent model, you have a so-called generate space-dependent model node, where you can select to set up a model in 1D, 2D, 2D axis, and 3D with chemical species transport, fluid flow, and heat transfer. I'm going to just quickly show you how that looks like in the graphical user interface. So typically you could start with a reaction engineering interface, and in the reaction engineering interface you can add reactions by just clicking the reaction button. Once you click that, then you can just type in the chemical equation right in the user interface. You can also type in actually chemical formulas, so CH4 and so on, but you can also use A plus B gives 3C plus D, like in this example. And then the rate expressions are automatically defined here. The reaction rates here are automatically set up using the mass action law. But you can manually, of course, change this completely. For example, if you want to remove the reverse reaction, you can just select the reverse expression and just have the forward reaction rate and so on. And so you can add a second reaction like in this case, and you can also add a generate space-dependent by clicking this button, a generate space-dependent model. In this case, I have generated a 2D axis model of a tubular reactor. And once I click create the space-dependent model, then the transport of concentrated species, laminar flow, and heat transfer in fluid flows interfaces are set up here automatically. Of course, I have to draw a geometry. And so once I solve the problem, for example, here, the time-dependent problem for the 0D problem, then the stationary problem for the 2D axis, then I can get the composition, the velocity field, and so on in this very simple and straightforward tubular reactor. So in that, using that strategy, you can very easily set up any type of model, including for non-ideal reactors, including both very complex chemical kinetics and also very complex transport processes. Yeah. One thing that I didn't show you here is that since this version, actually this latest version, we also have a thermodynamic property database in COMSOL in order to generate properties for liquids and gases such as heat capacity, thermal conductivity, binary diffusivities on mixture, and also to compute things like gas the composition of gases and liquids at equilibrium, so-called flash calculations. Density, viscosity, of course, and those properties that can be very, very hard to compute. They're actually not difficult. It's just a lot of work to compute. So you have a bunch of different thermodynamic models for liquids and gases, so that you avoid that sheer physical work that is involved in computing thermodynamic properties. So the rest of the presentation will actually be about tank reactors that are continuously stirred, They can be continuous, but they can also be batch reactors. So in this example, for example, a heated reactor, heated with those two pipes, vertical pipes, and with the bottom impeller, with a free surface also, a model using rotating machinery and with a free surface. And so in order to set up this type of problems in COMSOL, we have a number of ready-made so-called interfaces, fluid flow interfaces and reacting flow interfaces for rotating machinery. And there are several approaches that you can use. You can use the frozen rotor approach, and like in this case, the sliding mesh approach. In the frozen rotor approach, the impeller doesn't really move. You have a velocity at the blade of the impellers, but it's frozen in time. So it's a kind of pseudo steady state approach, which gives you a very, very a very good estimate of the flow distribution and the amount of mixing in a system. But of course, if for a more accurate estimate of the transport properties and of the variations of composition in space and time, then you can go with a full time-dependent solution using the sliding mesh. And so sliding mesh sounds very complicated, but it's not really that complicated. What COMSOL can set up any problem on a rotating domain, and what it does is actually just defines the equations under the hood in a moving mesh, using just the chain rule of differentiation. So COMSOL always generates for fluid flow, heat transfer, and so on, generates systems of partial differential equations. Now, if you're going to move the mesh, then what it really does is just uses the chain rule to compute all the differentials, the partial differentials, with respect to the moving mesh. That's what it does under the hood. So the ready-made interfaces for moving mesh, of course, are very easy to use, but you might as well add any type of phenomena or your own equations on a moving mesh and get this moving mesh automatically without having to do the work, the math for computing for expressing your equations on a moving system. And I'll show you this later. So there are a couple of things that you need to do in order to model rotating machinery or mixers, like in this case, or tank reactors, stirred tank reactors, using a moving mesh, a moving sliding mesh. And that's one of the things you have to start with, is to use assembly conditions for the geometry. And what does that mean? Well, basically, the core of the fluid, where the impeller that surrounds the impeller, that has to be a cylinder in COMSOL, and on that cylinder you tell COMSOL that that is one part in an assembly, and everything outside of that cylinder is another part of the assembly. So, and that allows on the faces between this inner cylinder and the outer fluid outside of that hypothetical cylinder, that the mesh over those internal surfaces does not have to coincide. That means that the elements do not have to share faces when you create the mesh. They can actually slide over each other, and the solution will be projected from one side to the other through interpolation. And so this is, of course, automatically done under the hood in COMSOL. The only thing you need to do is to tell COMSOL which domain will contain the rotating part and which domain will not contain the rotating part. And there are also other bells and whistles like internal walls, and those are walls that are very thin in reality, and so that would generate a lot of very small elements if you actually drew the real thickness in the model. So what you do instead is that you assume that it's just a surface that is infinitely thin, and you don't have to measure it then along the thickness. But you can have conditions on both sides of that surface, and that's what's called a so-called interior wall. And for frozen rotor, you can also use a so-called periodic condition. So if you have, in this case, in this figure here, what you can see is that you model 1/8 of the reactor or of the tank. And since the impeller here is frozen in time, you just apply a velocity at the surface of the impeller blades. That means that you can assume that you have periodicity on the vertical internal boundaries over the symmetry, the periodic conditions, where the periodic conditions are applied. And so that makes it possible to get very, very good estimates with a comparably very small computational effort, since the problem is only 1/8 of the original problem. So I'll show you a short demo of a mixer here in this case, but using how you set up a mixer problem or a batch reactor problem, a tank reactor with a central impeller, and how that is set up in COMSOL for sliding mesh and for a full time-dependent computation. So let's start with the first step. So what we need to define in definitions, this is actually new for version 5.3a, is that in definitions, you have a component, that's a three-dimensional component. And you can see that on the icon, which is a cube. If it's a two-dimensional model, it's just a square. Now, in the definitions, we have now centralized all the moving mesh. That means that whatever physics interface you add to this model, it will obey the moving mesh. It will actually be able to generate the equations for a moving mesh. And so if I had here manually added heat transfer and chemical species balances and so on, then they would all automatically get the rotating domain. In the past, you have to tell each physics interface where the rotating domain was. Now it's all centralized. So it makes it possible to set up multiphysics problem with one moving mesh feature, which is the one in the definition. And so here, the only thing I need to do is to tell COMSOL which one is the rotating domain. Now, the rotating domain here in blue, that's one of the two parts in the assembly. And the other part of the assembly is what's outside of the rotating domain, what you see here in red. And so in between the red and blue volume, these surfaces are so-called identity pairs. Identity pairs simply because the pressure and the velocity field and the composition is the same on both sides of these surfaces at one point on the surface. So in the rotating domain and in the stationary domain. And so that's the first thing we have to do in COMSOL. So the second thing we need to do when we generate the geometry, when we have generated the geometry, is this is actually the final step in the geometry sequence, They ignore edges and the mesh control faces after. They're actually added once the geometry has been created. And so the action that you need to do here is the default is to form a union. And so the internal part of the domain here, where the impeller is, the internal cylinder where the impeller is situated, and the parts outside. If we use a form union, they will be glued perfectly, and the mesh will be, the mesh elements over these two domains will coincide perfectly. All the elements on the surfaces between the rotating domain and the stationary will share faces. If I form an assembly instead, then I will allow the mesh to slide relative to each other on those surfaces. And when you do this selection of form assembly, and in console in this case only have two parts here, then what will happen is that identity pairs will be automatically created between these two parts. And so in the rotating domain, the only thing you need to do once the geometry is created is to actually tell how fast it rotates. In this case, how many revolutions per second, basically hertz in this case. And N0 here is just in the parameter list. And this is like a temporary database for data that we want to use in the computation. They don't mean anything until we use them. One nice thing about this is that you can actually type in the units for every parameter. So if I would do an error here in units, for example, if I would type seconds here, and then I go to the rotating domain, then you can see that I get an orange thing here. And so the use unit is second, but console expects hertz, 1 divided per second. This is a good thing to use so that you always attribute units to your parameters and to your inputs. Because if you forget a term in an expression, or if you make a typo in an expression, then what will happen is that you will see that as an orange input, and that will warn you that you will be able to solve that problem and you will not complain, but at least you get the heads up that you might have done a typo or something wrong. Now, if you do something completely wrong, that actually console cannot parse, then this becomes red instead of orange. So if I go back here and tell that it's actually 1 per second here, or hertz, and then go back to the rotating domain, then console will remove that orange color for the input, because then now it has the right unit. Okay. In this case, we're just using water, so we can load that from the database. And if we have more complex solutions, we can use the thermodynamic properties database if we have complex mixtures. But so to go back to the rotating domain and the sliding mesh, the only, well, I wouldn't say difficult, but if there's something I forget quite often is to set the flow continuity between these internal and the internal rotating domain and the external stationary domain. And so that has to be done by adding this flow continuity and by actually just selecting the identity pair here. There's only one identity pair created by the geometry when it realized that there are two parts, an inner and an outer part, and then the identity pair is the surfaces between these two parts. The mesh is then automatically generated, and if you look closely, you can see that since it's fluid flow and transport problem, it will automatically use a so-called, if we go back, it will automatically use a so-called boundary layer mesh, so that it will actually resolve the wall the flow at the walls a little bit better. And so once we solve the problem, then we basically get the fluid flow, and then we can also generate an animation from this. That takes some time, that we can. No, it didn't take that much, so we can repeat that. And so here we see the impellers. I should have had more time steps here to really see the rotation of the impellers. And here what you can see is qualitatively how the fluid flow distribution looks like. And this impeller actually works like it should. It's a so-called axial impeller. So it should, by its angle, it should generate an upwards and downwards rotating flow to obtain optimal mixing. This is actually a benchmark model. So this reproduces the fluid flow reported in a paper in the scientific literature. And so this is used to verify the solution of the equations, that we're actually solving the equations correctly here. And in this case, it's just we're using the standard K epsilon model here for solving this type of problem in COMSOL. So it's the K epsilon model for rotating machinery basically that is used here by default. So another thing that I want to mention is that, so now we saw here the time-dependent flow, and if we look closely, it already started with some kind of developed flow. We didn't have to wait and see until the flow was developed, and the reason for that is that we combined two studies. In the first study, we solved for a frozen rotor, so that the impeller in the middle doesn't really move. We just apply a velocity on the blades. Well, COMSOL does. We don't have to bother about it. We just select the static frozen rotor, and everything is done automatically for us. But what that gives you, it gives you a very good initial condition if you're interested in the harmonic steady state that you obtain. It's not a real steady state, but a harmonic steady state that you obtain once the impeller actually rotates. So you get a very nice initial condition for the full time-dependent simulation here that goes over 4 seconds. So you can see that when this, you will not see how the mixer or how the reactor behaves at startup, but you will definitely see how the mixer behaves once it has reached the operational speed. And so you see the amount of mixing, the concentration distribution that you could expect when you have reached the best possible mixing with this system. And so you will be able to see if you get the uniform product quality or not. And in that case, in this case, I guess the mixing is actually not very good. So what you would probably have to do is to insert another impeller a little bit up on the shaft, maybe on the middle, in order to get with some shift in the position in order to get an improved mixing at the top of the mixer or the reactor in this case. So to repeat again, first the geometry with form assembly. Form assembly separates the inner cylinder from the outer stationary part of the mixer. Secondly, define which part that is the rotating domain, and then tell COMSOL that you have continuity over these boundaries between the inner and outer domain. Set up the mesh, set up an initial solution with the frozen rotor, and then use that as an input to the time-dependent solver for the fully time-dependent solution of the problem. And then plot the solution, of course, and then a movie doesn't say that much, of course. It's just nice to see, and maybe some qualitative results and understanding you can get out of the movie. But eventually, what you do is you plot, you plot XY plots comparing some entity like the velocity against the norm velocity along, for example, in this case, the radius, or along and the viscosity, and you compare to experimental data and data reported by other people that have solved the same problem. So what are the typical customers that we have for this type of problems? Where the typical customers for the batch reactors and the stirred tank reactors are fine chemicals, pharmaceutical, consumer products such as soaps, shampoos, and toothpaste, and that type of problem. Food processing, that's also an industry where you find this type of batch reactors or tank reactors that can be continuous. And I already hinted that you have laminar and turbulent flows for rotating machinery. We have a bunch of different turbulence models, like algebraic turbulence model, transport equation turbulence models, and then ready-made functionality to deal with these rotating machineries. In the mixer module, we have a part library that I will show you also. And then we have so-called ready-made couplings for non-isothermal flows, reacting flows, and multiphase flows. So you can, right off the bat, set up a problem with rotating impellers and multiphase flow. And then you have all the other multiphysics capabilities. For example, you can couple the model that you see here to the left with a structural mechanics computation to see the loads and the stresses and strains that you obtain on the impellers, and maybe also the deformations on the impeller blades, and also compute the torque that will be required to drive these impellers. And there are a bunch of application library examples and so-called apps. And the one that I actually demo is in the application library. So you can download this example and actually run the step-by-step instructions to set up and reproduce the results that I showed you. If you look at the laminar flow capabilities, we have Newtonian and non-Newtonian fluids, and we use the Karuya-Suda model. But you can also type in any expression of the shear stress for your Newtonian models. We're also developing viscoelastic flow models for the next release that you can. And there's an example already now in the application library, but we will develop ready-made fluid flow interfaces for that. The turbulence models, like I mentioned, algebraic models, and then transport models like Spalart-Myers, K epsilon, realizable K epsilon, K omega, etc., etc. And I will actually walk you through those very quickly. So the algebraic models, like the Y plus and the LVL, they're very inexpensive computational-wise. They actually don't solve any transport equations for turbulence, and that's also the drawback. They're not very accurate for problems where the transported turbulence has a big impact. But those are models that are very popular when you have fluid flow and heat transfer, and so you want to have a good estimate of the energy consumption of a system, for example. And the temperature, and have a graph of the temperature distribution for quality control, etc., etc. And these are used a lot for example, electronics cooling, but also for mixers coupled to heat transfer. Then you have the workforce, which is the K epsilon model, and that is the reason why it's the workhorse is that it gives you relatively good accuracy for a relatively small computational cost. And so the one included in COMSOL has also realizability constraints, which increases accuracy. So it limits the amount of turbulence that can be generated in one point. There's also a more complex realizable K-epsilon model, which models the realizability in the coefficients. So that's a slightly more computationally expensive and also slightly more accurate. The K-omega model is implemented in COMSOL is the revived Wilcox K-omega, and it uses wall function for smooth and rough walls, but it has also automatic wall treatment, which means that if the mesh, like I show you, if you have a boundary layer mesh, and that resolves the boundary layer close enough, then what will happen is that it will automatically use a low Reynolds turbulent model that goes all the way down to the wall. So that's, needless to say, that's more computationally expensive, but also if you have the required mesh resolution, then it's also more accurate, of course. SST is a combination of K-epsilon and K-omega. So it takes the best of both worlds, close to the wall and far away from the wall. The low Reynolds K-epsilon turbulence model, that requires, of course, a mesh resolution, because it always solves the problem all the way down to the wall. And it doesn't assume a boundary layer where you set the conditions outside of the boundary layer. It goes all the way where the velocity is zero. The V2F turbulence model is more complex and also a more expensive model. And what it does is actually treats the anisotropy of turbulence. So if you close to the wall, you get a different turbulence parallel to a wall compared to in the direction perpendicular to the wall. And so that is very common for curved surfaces. And so in that case, the V2F turbulence model, which is a 4-equation model, so it's basically K and epsilon and two more equations to model an anisotropy. That is more expensive, but of course very accurate. Palatal mass is used for aerodynamics. So if you have turbulence flow, for example, in gases with kind of a type of impellers that look more like propellers or ventilators, then that's probably decent and relatively inexpensive model to use. It's a 1-equation model. It's a low Reynolds model, so that means that you have to go all the way to the wall. So in that sense, it's somewhat expensive, but other than that, it's relatively inexpensive, I would say. Now, if in the mixer module, you can set up a huge number of combinations of different impellers. Although they're actual impellers and radial impellers, and then some kind of high viscous fluid impellers, both the actual and the radial impellers can be generated in many different combinations. So there are 11 impellers, but you can create everything from a propeller to an impeller using using the fact that you can actually create fillets and chamfers, and you can also fold the impeller surfaces along a line by just telling the part library that where you want to fold. So you can create these type of impellers. For one actual impeller, you can create a huge number of different types. These are just a few. And then the radial impellers, of course, needless to say. The two impellers for highly viscous fluids are those. This is the standard. This is a standard impeller, an Encato impeller, and this is a typical impeller that you would use, for example, to mix paints and very highly viscous fluids. It could also be used in the food industry and the food processing industry, these type of impellers. And so using the mixer module, you have 3 basic parts: the impellers, the shaft, and the tanks, different types of tanks with cone-shaped bottom, with dish formed buttons but dish button impeller tanks, or you can also have just flat button. And you can combine those by just loading these geometries from the geometry part library. You don't have to build them. So they're fully parameterized, so you can vary radius and you can vary length and you can vary, of course, height and thickness of parts and so on. And you can also vary radius of fillets, position of chancers, and position of folds. Like here, for example, you have a fold. That fold can be positioned wherever you want on the impeller itself. This is a 2D tutorial for rotating machine and non-isothermal flow, which you can do very well up to for fully compressible flow for max number below 0.3, where you don't have to account for shocks, for example. And you can the heat transfer, like I mentioned before, that can be modeled both in the fluid and in the solid parts, and you can have that fully coupled simultaneously model, for example, for a time-dependent problem. And there are ready-made interfaces for reacting flow, for both for laminar and turbulent multi-component transport. And of course, for laminar, you can use very accurate models like the Maxwell-Stefan multi-component transport models, and you can use mixture average model or just pure Fickian models for diluted solutions. And you can also have electrochemical problems with electric fields for migration of charged species, so that you account for that also in the transport of chemical species, fully coupled to fluid flow and, of course, chemical reactions. And since the last version, we also added mixture and bubbly flow as ready-made interfaces for rotating machinery, and where you can model solid particles or liquid droplets in a fluid, or gas bubbles in a liquid, for example. And you can, of course, do this for laminar and turbulent flows. I briefly mentioned fluid structure interaction in order to compute things like torque or stress and strains on the impellers. The conjugate heat transfer, I already showed you, and the reaction engineer, of course. That's needless to say. That's I wouldn't even call it a multiphysics coupling. It's just a reacting flow, or just what you expect from a package for chemical engineering and transport phenomena, which is what we have here. One thing that is nice to have is the particle tracing module, because there you can do very complex multiphase flow using Lagrange spoiler models with a two-way coupled two-phase flow, and also charged particles. Of course, that you can only use for a small amount of particles, but it's still a very inexpensive way of modeling two-phase flow. And so everything that I showed you here is available for you to reproduce in the application library with step-by-step example, with step-by-step instructions. And the one that I showed you, which is shown in this movie, is actually the World-Jet 4-pitch plate impeller model that is included in the application library. There is also in the mixer module a very nice little app, which is an example of what you can create. So once you have set up a model like this, which is it's not very difficult to create for an expert in the field, of course, like most of you probably are. You're experts in modeling. Once you have set up a model like this, then you can create a very simple graphical user interface by using the application builder. And so the application builder basically allows you to drag and drop graphic widgets to create a user interface. You can create a form where you input an impeller diameter, for example, and then you have a button to compute the solution. For example, compute one of the study steps. And then you might want to displace display one of the results, for example, the velocity field. And so this allows you to basically create a very, very easy to use little app. If we might want to use a smaller button. And if somebody wants to change the impeller diameter and press equal to solve the problem, then you can generate a very easy to use user interface only for that type of problem. So you give the instruction, okay, here you change the impeller diameter, then click compute and then evaluate the result, and that's it. Yeah. And so this is, of course, a lot more complex than the little example that I set up in 10 seconds, but it allows you to choose from a huge number of impellers and also to position them in whatever way you want inside the dish bottom, the flat bottom, and cone bottom type of tanks that we have. And everything is, of course, fully parameterized, and you can select operating conditions and physical properties of the liquid and so on. All right, so I think we're out of time, and so we have time for questions. And here is, you can contact us also at console.com, and you can also mail me at console.com. It's very easy to remember. And so, I'll stop sharing my screen, and it's time for questions.
Okay, thank you, Ed. Let me just get to a screen. We can stick with that. So, first question. For optimum mixing, what mesh concept, for example, sliding or fixed mesh concept, is preferred? Or is the selection based upon the characteristics of the fluid medium?
Yeah, that's a good question. It more depends on your expectations. So if you know that is not extremely crucial to get a very high accuracy for product quality, for example, you only need to know the degree of mixing, plus minus 10%. Then you might probably get away with frozen rotor. But if you want a highly accurate model at every time step and in space, then you have to go to the full time-dependent sliding mesh solution. And with that said, once the flow is turbulence models are inaccurate in nature. So you cannot expect a very, very large accuracy for a turbulence model because there are simplifications of the real problem. And so then the probability that you will get away with a frozen rotor model is larger. And so the frozen rotor approach is very popular when you're dealing with turbulent flows, because since you already lost a lot of the accuracy due to the turbulence model itself, then the fact that it's not completely rotating, sure, it adds to the loss of accuracy, but maybe not a lot. Yeah, but that has to be decided on case by case, depending on the accuracy that you want and that you expect from the model.
Okay, thank you. How does this modeling technique apply to a non-Newtonian viscoelastic fluid?
Viscoelastic fluid. You can use the exact same technique, actually. So in this case, like I said, any type of physics or any type of equation in COMSOL can be formulated on the moving mesh. For a viscoelastic problem, of course, you have additional equations to the one that you have here. And so there is actually a problem in the application library. But in principle, the way of setting up the model is analogous to this. It's very close to what we showed today.
Okay, thanks. I have not used COMSOL in a long time, but I remember not being able to model nuclear waste. Lots of metal salts and nuclides in water. Can it do that now?
Can you repeat that? Lots of metal?
Lots of metal salts and nuclides in water.
Okay.
Can it?
Okay. I mean, nucleids. So it's solutes basically. So you're dealing. I guess you want to deal with solutes in a solution, a high concentration of salts in a solution, and so that depends what you mean with modeling. So if you want to treat the transport of these species, for example, using concentrated electrolytes, then COMSOL does have that. So I would guess without more information that you surely should be able to model that type of problem.
Okay,
unless you mean the radiation problem itself, but I guess you're not. I guess you mean the transport of salts of species in an electrolyte, basically.
Okay, thanks. Can COMSOL be combined with the residence time characteristics to determine the nature of non-ideal flow in the tank, such as bypassing, channeling, and so on?
Yeah, that's a very good question. So actually, I'm thinking about making a tutorial for exact that type of problem, because what you need then is that, you have a residence time distribution curve, and so in the COMSOL model, what you would have is to have an inlet where you send in a pulse, and then you will look at the outlet, how that looks like, and then you would validate that with experimental data. So we're actually developing a product that includes the residence time curves obtained from experiments or in whatever way that you want, but also so that you can model a full 3D fluid flow problem with solute transport and generate that residence time distribution curve, so that to use that in a much simpler zero-dimensional model, like the type of lump model. So you use a complex computation to generate a simpler, more or less lookup model for the residence time distribution. So you can absolutely do that. Absolutely, yeah.
Okay, thank you. Can you explain more on what the identity pairs are for an assembly of moving mesh?
Yeah. I guess that was not very clear. But so what it means to say that you have an assembly is that you have two parts, two basically three-dimensional objects that share a surface. It could be a curved surface or a flat surface. They share that surface, but using assemblies, that surface will actually be two surfaces, one for the object on one side and one for the object on the other side. So that's an assembly consisting of two parts with two individual surfaces. So the two, they seemingly share one surface, but in geometrically, they're two completely watertight, separate geometrical objects. So what the identity pair does is that it tells COMSOL, okay, we don't want to have the same mesh on these surfaces. We want them to have completely independent mesh on both sides of this common surface. But the solution on both sides in one point should be identical. Of course, so because it's a fluid, that surface in our case is not there in reality for the rotating domain and what we call the stationary domain. In reality, there's no such surface. We just use it in order to slide the mesh. So the identity pair says that, okay, the solution on this side of the surface should be identical to the solution on the other side of the surface. Yeah. So that's an identity pair. Okay. I hope that was a better explanation than during the presentation. Yeah.
Okay, thank you. Will COMSOL optimize the study, physical geometry or RPM temperature, based on some parameter going maximum or minimum?
Yeah, that's a good question. So that's also a good question. You cannot. So in this little app, we have different measures of the degree of mixing, And of course, you can use these numbers or measurements in the model to optimize. If you have some kind of critical derived value that you have to avoid or that you want to optimize, then you can actually have the variables that you want to vary and find the minimum or maximum of the measured value, the derived value that you want to optimize upon. For example, assume that you want to minimize the distribution between the maximum and the lowest or highest concentration at different points in the reactor, so that it should be a minimum. Then you set that difference as a derived value, and you can then, for example, change the impeller radius or the position of the impeller in order to minimize that. And that you can do with a parameter, and that parameter will be perturbed by COMSOL until it finds, and of course with a kind of smart, intelligent algorithm, in order to find what value of that parameter that actually minimize the difference on the concentration between 2 points, for example. And so that can be done in combination with the optimization module. Yeah.
Hey, thank you. What variable are we looking at with the color code? Velocities?
No, you can plot anything. So any expression, we looked at velocities, but you can type in whatever expression. You can type in the expression for the stresses in the fluid. You can type in the expression for the concentrations, the reaction rates, whatever you want. Actually, you just type it in, just like you would, write it with pen and paper. Whatever expression you wanna plot, you just do it. You just type it in.
I think, can we have a source and sink in the mixer models?
Yes, you can. And actually, there's different types of source and sinks. So, for example, one way of modeling an impeller is to actually not draw the impeller. It's to just replace the whole impeller with just a cylindrical shape that would surround that impeller, just the impeller blades, and then add a momentum source inside with a direction. And so that if you know what type of flow the impeller will create, then you can have, instead of geometrically drawing the impeller, have a momentum source with a direction and even a time dependency to do that. Then you avoid a lot of problems, of course, also the moving mesh and so on. Yeah. So that's possible, absolutely. And you can, of course, in sources and sinks that are chemical reactions, you can of course also have, and you can simulate also a sink of mass. If you have a pipe that is very small and you don't want to draw it, you can just add a cylindrical shape where, okay, here's the pipe and that's a heat mass sink. The mass disappears through that hole. And, so you can do that, of course. Yeah.
Okay, thanks, Ed. I'm sorry, but that's all the time we have for questions. So if anyone in the audience still has a question that wasn't answered, they can go ahead and send it to me at producer@aiche.org, and I'll forward it on to Ed. So now, on behalf of the American Institute of Chemical Engineers and everyone who attended today, I'd like to thank Ed Fontes for this informative presentation. Thanks also to our participants for your cooperation and thoughtful questions. Please visit aiche.org to replay this session or to view and sign up for our many others. Goodbye. We hope to see you again in a webinar soon.
Bye-bye. Thank you very much for listening. Bye.